yes. So roughly around the same time that Wald wrote his famous paper. Oh yes, there's something else that I need to tell you. And the other thing is that for a general surface like that, you would obviously expect that there would be corrections to this this entropy functional, and you write down all possible corrections. There would be all kinds of bulk Ricci scalar. There'd be also some contraction of the bulk Ricci tensor with the ends in some way, and then also some contraction of the bulk Riemann tensor with the ends in some way, and then also there would be K's, the extrinsic curvatures. So that would be a most general entropy functional that you would write down. So imagine that I gave you an entropy functional that works for this. So in this example that I did, I worked. So what is the procedure that I followed? So I wanted to work out the equation for f of z, but then in order to work out the equation for f of z, I need to integrate by parts. Because for this particular case, generically there will be f double prime that appears in your action. So in order to work out the equation of motion, I need to integrate by parts. So by integrating by parts, I assume that there is a suitable given Hawking term, which allows me to throw away the surface terms that I get from integration by parts. And for a general theory, a suitable given Hawking term does not exist. It's not even clear whether for a general theory like this you can write down an ideal function of this kind, whether it makes sense. You'll be able to write it down, but whether it makes sense is a different question. But for a particular case, which is Gauss-Bonnet, this is the Gauss-Bonnet action. It turns out that there is a proposal that gives you the right result. This is simply the area functional is just this. This curly R that I've written down is just the intrinsic curvature of this three-dimensional surface. Okay, and for this action, there is a suitable given Hawking term. It's simply twice lambda L squared. Okay.
Isn't there a paper by Qigong where he?
Yeah, I mean you can always write down area functionals. There's no question. There is nothing stopping you from writing down an area functional.
He claims he has a result for any theory.
Yes, yes. So I mean even Sorodukin and Kursai and Pakshushit, they give you the general area functional for this guy. It gives you the right universal terms and so on. But then, so again, you're making an implicit assumption that there is a suitable given Hawking term. Okay. Anyhow, so this particular action has a name because this was worked out in the black hole context first by Jacobson and Myers, and so it's sometimes referred to as the Jacobson-Myers function for this Lovelock theory. It differs from whatever result Wald gives you precisely by these extrinsic curvature terms. The extrinsic curvature for black hole horizon vanishes, so both Wald formula and this would give rise to the same result for black holes and for spherical entangling surface. But for when you have extrinsic curvature like the cylindrical entangling surface, it is this object that produces the right result. Actually, you can do a little bit better than that. You can actually show, and unfortunately I don't have time to go through that proof because it will take me another hour. So there is an argument due to Likovich and Maldacena which tells you how to derive the entangling surface equation starting from some given action, and you can show that the entangling surface equation that you get for this Gauss-Bonnet action using the procedure is actually the same as whatever would come from this action. Okay. So you can say that if you believe the arguments of this paper, then there's a derivation for this entropy function. So since you raised the question about whether it's guaranteed that it's going to close off smoothly in the interior, because it will be a nonlinear equation in general, let me just tell you something. So if you start out with this particular entropy functional, and you build the same calculation for the sphere case, do the argument that I presented there, that you assume that it closes off somewhere, work out the initial equation and see whether what the roots are and so on. For the spherical entangling surface, it turns out again that that's the only solution that exists. That's again an exact solution to this problem as well. But for the cylindrical entangling surface, there are more solutions. Okay, so there are more solutions. In fact, you'll get something, so instead of closing off like this, it does that. And not only that, in order for, so what you do is you plug in an ansatz like this. The slope of this actually tells you whether these two branches meet at right angles or not. If the slope didn't have the right sign, instead of getting this, you'll get that. And so this has to be of a certain sign. So this, whatever number that sits in front, this has to be greater than 0 when alpha is half. And it turns out that for the cylindrical case, this actually puts constraint on allowed value for lambda. Lambda is constrained. You might ask, what do I mean? What do I do with that constraint? Just because we have Diego in the audience, let me just tell you that there are some independent arguments due to him and Juan Malacena, and also due to Myers and Kuchel, which tell you that lambda cannot take on arbitrary values. So the argument that they used had to do with demanding positive energy correlations. So this has to be positive. So you're doing some thought experiment on the boundary theory. You're turning on a disturbance. It propagates all to infinity. There are detectors that are sitting there. Each detector measures some pulse, and then you want to demand that the expectation value of the energy is positive. That gives rise to constraints. It turns out that I don't remember this. You remember numbers? I think this is 9 over 100, and this is minus 7 over 36.
So you do remember.
Eh?
So you do remember.
Yeah.
Somebody read your paper.
Yeah. So this was a pure CFT argument. These numbers that you get, and there's a holographic story as well. Both of them give rise to the same result. So in terms of the CFT, actually what they found, if I remember correctly, they defined this quantity C minus A over C, this delta, and this delta had to lie between minus a half and a half. This was for, I think, well, n equal to 2 supersymmetric theory is 1. N equal to 1 supersymmetric. Both these coincide. It's a coincidence, I think. Okay. Any other questions you have so far as this particular story is concerned? Oh yeah. You might have wondered whether this bound that you get by demanding this kind of an argument, how does it compare to this? Actually, this bound is weaker than this constraint. So if lambda, this constraint is like that, the constraint that you get by demanding or making arguments of this kind, that the surface closes off smoothly, is somewhat weaker.
What is it on the positive side, you remember?
It's very close to 9 over 100 actually. So on the positive
okay.
side is 7 over 64 or something like that.
Okay.
It's not too far from 9 over 100. Okay, so let's move on to relative entropy. I have, 20 minutes? Okay. Let me begin by showing a particular formula. I want to derive this result, rho 1 over rho naught, and I'll explain to you what these mean. Delta H minus delta S. So the left hand side, if you remember, was trace of rho 1 log rho 1 minus trace rho 1 log rho naught. At this stage, I can define a density matrix, and this is a purely formal definition. I can always write the density matrix because it's Hermitian and positive semi-definite. I can always write this as e to the power minus h. When you write a density matrix in this form, h is referred to as a modular Hamiltonian. This is what algebraic field theorists would refer to this as, and apparently condensed matter theorists refer to this as the entanglement Hamiltonian. Well, actually I need to normalize this, so these are all normalized so that the trace is 1. So this is what it is. Okay, so now suppose we define a quantity f of rho that is trace of rho h minus t of s of rho. So this s of rho is the von Neumann entropy corresponding to the this density matrix. So that f of rho 1, I'll tell you what t is. T in this particular case is just 1, but let me just keep it there anyway. So trace f of rho 1 is trace of rho 1 times h minus ts of rho 1, and this is f of rho naught is trace rho naught minus t rho naught. So you can consider, and I'll put in quotations, the thermal density matrix. Suppose rho naught you wrote as e to the power minus h by t. So I've put this in quotations because the way that I wrote rho here, this also looks like a thermal object with temperature 1. That's why I put it in quotation marks. It need not be the true thermal density matrix. So for the modular Hamiltonian T is 1. Then you can do a simple algebra to show that delta of h is, well, first let me go through this algebra because I think that will probably be the most useful thing that I'll be able to communicate given the times. So h over t from here, from this equation, it just follows that this is minus log rho naught minus log trace e to the power minus h over t, and so rho 1 times that is just rho 1 and rho 1, and so that enables us to write this to be equal to 1 over t trace rho 1 h minus trace rho naught h plus trace rho 1 log rho 1 minus trace rho naught log rho naught. This is just the definition of these objects that I wrote down there. And then I get this to be equal to minus trace rho 1 log rho naught minus trace rho 1 log trace minus h by t plus trace rho naught log rho naught plus trace rho naught log trace e to the power minus h by t, and then plus trace rho 1 log rho 1 minus trace rho naught log rho naught. So that term and that term cancels off. These are normalized density matrix, so that is off. That is 1. This is also 1. So that term and that term cancels off, and so you get this to be equal to S of rho 1, the relative entropy. This is exactly equal to relative entropy. And then if you define delta H to be trace of rho 1 times H minus trace of rho naught times H, so that's the definition. delta S is S of rho 1 minus S of rho naught. So that is what I mean by so this quantity is just equal to that. So this F of course reminds you of a free energy. So this is just telling you the positivity of the relative entropy is just telling you that it is the thermal density matrix that is going to minimize. That is going to have the least amount of entropy. Okay. So what do you do? What do you do with this? So the reason why I was doing this, the reason why I wanted to write it in this form is because this is nothing but the expectation value of the modular Hamiltonian in state 1 minus the expectation value of the modular Hamiltonian in the original state, and this is the difference between the entanglement entropy corresponding to state 1 and the original state. So on the ADS safety side, we know exactly how to calculate this here. For very specific entangling surface, we know the expression for the modular Hamiltonian. So only for very specific entangling surface is the expression for the modular Hamiltonian known, and the sphere is one such entangling surface. For the sphere, the Hamiltonian is 2 pi v3x r square minus r square over 2r, and the 0, 0 component of the stress tensor. And it is this quantity that we can calculate using holography. So I went through the rules yesterday. You just do the Stefan-Graham expansion, and then for Einstein gravity, it is just the coefficient, the time-time component of the coefficient of the Z4 correction. So you can calculate delta H, and now you can also calculate delta S because you've got a proposal for the entropy functional. And now you can check whether actually it is true that this is positive. So if this is positive, this would mean that delta H must be bigger than or equal to delta S. And then you can carry out this check case by case if you want. I mean, a priori, it's not even clear what in the theory of gravity ensures that this inequality is respected. So you might wonder, is there some energy condition? Is it some maybe some causality constraint? What in the theory of gravity knows about this inequality? Okay. Now, of course, now you can play all kinds of games because you can easily consider a small perturbation away from ADS5 that will give you a new state rho 1, and because it's a small perturbation, you can do things in a controlled fashion, and then you can check this inequality, you can compute things and see what happens. So now I don't have time anymore to go through the examples that I wanted to ensure, but then I can tell you some of the results. So you can consider an excited state. So rho 1 could be an excited state where you're perturbing the original ADS 5, the bulk metric, by a constant stress tensor. The interesting case, in my opinion, is when you do it for this higher derivative theory, because you can distinguish the central charges that appear in the game. So for this constant stress tensor case, again, you have to do a bit of work because you have to work. So what you need to do is you need to carry out the expansion for the boundary metric up to second order. So it looks like some eta mu nu plus some t mu nu z z square, and then there's also some second order term. So it's t mu alpha. And you can expand up to the second order in perturbation, and because only at the second order in perturbation do you get an inequality. If you just consider the linear order in perturbation, you get an inequality. That is very easy to see. that suppose you had some continuous parameter lambda that connected you to your original density matrix rho naught. So lambda equal to 0 was your rho naught. Then what you can see is that if lambda was slightly positive, this quantity is bigger than 0. So lambda slightly positive. This is lambda. This is this quantity trace of rho 1. This is S. So this is S. This is the relative entropy. So lambda slightly positive is bigger than 0. So lambda slightly negative again is bigger than 0. So this is lambda equal to 0. So again bigger than 0. And at lambda equal to 0, because of this condition, it is 0. So you get a graph like that. But this is saying that at lambda equal to 0, there is a minimum. So that would mean that because this is equal to delta H minus delta H minus delta S does not have a linear term in lambda. And this means that to linear order, delta H is equal to delta S. And that's exactly what you can really verify. That's why you need to go to second order in perturbation to see anything interesting. It turns out that in whatever analysis that we've done till now, in all cases, this particular relation, C was the one of the anomaly coefficients. This is also what appears in the 2-point function for the stress tensor. This bigger than 0 guarantees that that inequality is satisfied. So there are a whole bunch of other interesting things that you can do. We're trying those things out right now. Try and answer this question whether this condition alone is sufficient to guarantee this. Okay? It would be nice if it was more exciting than this. Maybe you get some inconsistency. It will be nice to see whether this can be used to get some interesting bounds. Okay, so let me just conclude with some remarks. So far as this entanglement entropy is concerned, on the holographic side, I think that there are several interesting problems. So whatever I've discussed till now, I have discussed it for the static situation. The more interesting case is, of course, when rho, the density matrix, is a function of time. And in that particular case, I think the situation is much murkier. There's no proof. There's no really arguments to. So for time-dependent cases, it's less clear. There's no derivation. There is a derivation for the static case. In fact, Diego pointed out that there's some conjecture that the analog of the world formula for any arbitrary theory of gravity has been given recently. It's not really clear whether how I mean, lots of checks need to be carried out before we conclude that is the correct thing. But I think the most pressing thing is to understand for time-dependent backgrounds. And then of course, what exactly is this? All these calculations teaching us? So there's some interest in trying to rewrite Einstein equations. In terms of entanglement entropy. What that is going to teach us is not completely obvious to me, but that is very similar to a proposal that Ted Jacobson had in 1995, where he was able to use thermodynamics to derive Einstein equations. So seems like there's a lot of open problems, a lot of questions that one can try and address. Yeah, so I think I'll stop there and let me know if you have any questions.
Questions or comments?
So the entropy functional itself is different. So the entropy functional, instead of being just square root of h, it starts depending on the curvature tensor. So there's a metric, there's a pullback metric on the entangling surface, and then the entropy functional in this particular case for the Lovelock theories, it starts depending on the intrinsic curvature of that surface.
Can you explain around those two episodes?
Oh yeah, okay, yeah, I can do that. So you're talking about the solutions, yeah. So in that particular case, the starting point is of course this square root of h 1 plus lambda square this object. It turns out that for the spherical entangling surface, this is still an exact solution for whatever equations follow from that functional. For the cylindrical entangling surface, up to this particular order, there is no. So you might have thought that there is a lambda parameter that appears here. So in the solution also there will be maybe some lambda dependence. So up till this order, there is no lambda dependence. The lambda dependence starts appearing at a higher order. Okay. And yeah, so the lambda dependence appears here. So C of course depends on, because I told you that for Einstein gravity C and A are equal. It's only for higher derivative theories that they are unequal. And so that is what enables us to distinguish A and C. So although the solutions do not depend on lambda, because of the lambda dependence in the functional, these coefficients start depending on lambda. I'm sorry? Now capital H is the length of the cylinder, yes.
Any more questions?
Yes.
Yeah.
So yesterday you mentioned the monodromy property.
Yes.
It can also be shown in a similar
Yes.
way.
For large n theories, it turns. I mean, for this, the same argument that it did there can also be shown for monogamy of entanglement. So there is, but it may be. So the understanding is that it could be a large n artifacted. It's not clear whether it holds in quantum field theories or not.
So you have this first law, delta H equals delta S. Is it true that that also non-equilibrium states?
Yeah, so if you, if you, for non-equilibrium states, so rho as a function of t. So I think whatever in the derivation, in the way that I recast, whatever statements I made here, I did not need to assume that rho was independent of t. So yeah, so I would say yes. So at that level.
I see. I guess I'm asking because in the Jacobs argument, he claims that if you consider higher curvature corrections, there is a correction to the first law, and he says that's non-equilibrium and things like that. That's what he says. So
here,
okay,
we can go
but
through the arguments.
so that law is in a sense more general than the usual first law.
Yeah. Probably, I mean, the argument that I presented there, I did not need to assume that rho was independent of t anywhere. It would seem like.
Any other questions? Well, if not, let's thank Aninda for all his very nice lectures.